There are basically two types of vector multiplication. One is called scalar product or dot product, and another is called vector product or cross product. In scalar or dot product, we write a dot in between the two vectors that are multiplied. The result is a scalar, which has quantity but no direction. For example, the dot product of a vector A and vector B is equal to the product of their magnitudes multiplied by the cosine of the angle between them, which is theta in this case. Now let's think of a force acting on a body which is placed on a horizontal surface, making an angle theta with it. Now this force causes the body to move horizontally in this direction like this, which moves by a distance d. The force can actually be resolved into two components. One component along the direction of the displacement of the body, and another component will be right angles to it. Clearly, the horizontal component, which has magnitude f cos theta, is responsible for the movement of the body and not the vertical component, as there is no vertical motion of the body. As we all know from the knowledge that we got from our physics classroom, that work done is the force times the distance, where force means the magnitude of force in the direction of displacement, that is f cos theta. So this is the formula that we get. Notice carefully that we can easily think of the displacement d as a position vector d, this being the initial point. This line can also represent the vector f, which is force F applied on the body. We just redraw the vectors like this. The angle between them is theta. The dot product of these vectors is this. Now we notice that these two values are same. So we understand that the work done is actually the dot product of the force vector and displacement vector. This is quite understandable, as we can easily perceive that work done is really a physical quantity which has magnitude only but no direction as such. Geometrical interpretation of scalar product. Let A and B be two vectors and the angle between them be theta. Then their dot or scalar product is this. Now draw a line BL perpendicular to vector A. Then OL, which is the projection of B on A, is equal to mod B cos theta, and OA equal to mod A. Therefore, A dot B is equal to OA into OL, which is equal to magnitude of A into projection of B on A. Properties of scalar product. Commutative. Look at the diagram. Here, A dot B equal to magnitude of A into projection of B on A, which is equal to OA into OL, which is equal to OA into OB cos theta, and B dot A equal to magnitude of B into projection of A on B, which is equal to OB into OM, which is equal to OB into OA into cos theta. Therefore, A dot B equal to B dot A. Distributive over vector addition. Here, OA equal to vector A, OB equal to vector B, and BC equal to vector C. Clearly, from the triangle law of vector addition, we get OC equal to B plus C. Now, A dot B plus C is magnitude of A into projection of B plus C on A, which is equal to OA into OM. And A dot B plus A dot C is equal to magnitude of A into projection of B on A plus magnitude of A into projection of C on A, which is equal to OA into OL plus OA into LM, which is equal to OA into OL plus LM, which is equal to OA into OM. Therefore, A dot B plus C equal to A dot B plus A dot C. From this property, we may easily prove that A dot B minus C equal to A dot B minus A dot C. Scalar multiplication property can easily be proved by the facts that if a vector is multiplied by a scalar, only its magnitude changes, not its direction. So the angle between two vectors remain the same even if any or both of the vectors is multiplied by the scalar. When the dot product of two non-zero vectors is equal to 0, then the vectors are perpendicular to each other. This is called the orthogonal property and can easily be proved by the dot product formula. A dot B equal to mod A into mod B into cos theta, which is equal to 0. Since mod A is not equal to 0 and mod B is not equal to 0, therefore cos theta equal to 0 or theta equal to 90 degrees. From this property we may interpret that these dot product of unit vectors I cap, j cap and k cap along x, y and z axis respectively is always equal to 0. This property we see that the dot product of two same vectors is equal to the square of the magnitude of that vector. This can easily be proved by the fact that two same vectors are parallel vectors and angle between them is 0, and that the value of cos 0 is 1. From this property we may interpret that these dot product of unit vectors is equal to 1. These properties can be proved by taking into account the properties discussed earlier like this. You can get the proof in any standard textbook on vector algebra. Scalar product in terms of components. If vector A equal to A1 I cap plus A2 j cap plus A3 k cap and vector B equal to B1 I cap plus B2 j cap plus B3 k cap, then A dot B equal to A1 B1 plus A2 B2 plus A3 B3. This can easily be proved like this by using the properties of scalar product that we have already learned. Angle between two vectors. Angle between two vectors is given by this formula, or more precisely this one, when the concerning vectors have been given in component form. Deriving the cosine law. In this triangle, as per cosine law, c square equal to a square plus b square minus 2ab cos theta, where theta is angle BCA. We are going to prove this by vector method. Let CA equal to vector B, AB equal to vector C, and CB equal to vector A. As per triangle law, CA plus AB equal to CB, or AB equal to CB minus CA, or C equal to A minus B. This implies C dot C equal to A minus B dot A minus B, or mod C whole square equal to mod A whole square plus mod B whole square minus 2 mod A mod B cos theta. Finding the component of a vector along and perpendicular to another vector. Let OA equal to vector A, OB equal to vector B be two vectors. We are going to find the component of B along and perpendicular to A. For this purpose, we draw line BL perpendicular to OA. Then OL will be the component of B along A, and LB will be the component of B perpendicular to A. Now vector OL equal to mod OL into A cap, where A cap is a unit vector along vector A, which is equal to mod OB cos theta into A cap, which is equal to mod B cos theta into A cap, which is equal to mod A into mod B cos theta A cap divided by mod A, which is equal to A dot B into A cap divided by mod A, or OL equal to A dot B divided by mod A whole square into A. This is the component of B along A, and vector LB equal to OB minus OL, which is equal to B minus A into A dot B divided by mod A whole square. This is the component of B perpendicular to A. Vector product or cross product of two vectors. In vector or cross product, we write a cross in between the two vectors that are multiplied. As we all know by now that two vectors A and B are coplanar, and let angle between them be theta. The cross product of the two vectors is equal to mod A into mod B into sine theta into n cap, a unit vector, such that n cap is orthogonal or perpendicular to both vectors A and B in such a manner that vectors A, B and n cap form a right-handed system. By right-handed system, we mean to say that if we keep our right hand on the vector written on the left-hand side of the cross sign, that is vector A, in such a way that we may curl our fingers other than the thumb towards the vector written on the right-hand side of the cross sign, that is vector B, then the thumb points at the direction of vector n cap. The magnitude of cross product vector is equal to this. Now let's take a practical example to explain cross product. If a force F acting on a wrench to loosen a nut at a distance r from the axis of rotation of the nut, which is denoted by point O in this diagram, which is also called the pivot point, then the torque tau generated in the nut will cause the nut to rotate counterclockwise in this case. The torque therefore will have a direction upward because the nut moves up. Now the magnitude of torque will depend on this distance. Now if we apply the force nearer to the pivot point, in that case torque generated will be less and it will be more difficult to open the nut. So as the distance is decreased, the magnitude of torque decreases. This distance is called the moment arm and is equal to r. Let the angle between the moment arm and the applied force be theta. The torque will also depend on the magnitude of force. It is obvious that all of the force F is not responsible for the torque generated. Just like dot product example, we will resolve the force into two components. Here the component along the moment arm is F cos theta, which does not contribute anything to generate the torque. This is quite obvious because whatever force we may give in this direction, the nut will not rotate. In fact, this component will pull the wrench out of the nut. The force perpendicular to the moment arm F sine theta, which is fully responsible for the torque generated. So magnitude of torque tau is equal to R into F into sine theta. The direction of the torque is got from the motion of the nut, which is upward. Now we may consider this moment arm as a position vector of the point where the force is applied, the pivot point being the initial point. This is represented by vector R. The force F can also be represented by vector F. Now we redraw the vectors like this. The motion of the nut is upward, which is the direction of torque, and will represent the vector tau. Clearly, the three vectors form a right-handed system. So it is quite obvious that torque is equal to the cross product of vector R and vector F, and eta cap is a unit vector along vector tau. Remember that this unit vector only defines the direction of the cross product, and this part is the magnitude of the cross product. Since the cross product of two vectors have direction perpendicular to both vectors A and B, therefore three-dimensional real coordinate space is mandatory to solve problems on cross product of vectors, while dot product of vectors may be solved in both two-dimensional and three-dimensional real coordinate space. Geometrical interpretation of cross product. Let A and B be two vectors. Angle between them is theta. Draw the parallelogram OACB. This is the cross product of A and B. The magnitude of the cross product is this. Here mod B sine theta is the height of the parallelogram and mod A is the base of the same parallelogram. Thus magnitude of cross product is equal to the area of the parallelogram whose adjacent sides are represented by vectors A and B. The direction of cross product is a vector perpendicular to both A and B such that these three vectors form a right-handed system. We also come to know that half the magnitude of cross product is the area of the triangle OAB. Properties of cross product. It is not commutative. A cross B is not equal to B cross A because here A, B and unit vector n form a right-handed system, and here B, A and unit vector eta form a right-handed system. Clearly n and eta are unlike parallel vectors having exactly opposite directions. Thus A cross B is equal to minus B cross A. Scalar multiplication. These properties may be proved by the knowledge that when we multiply a vector by a scalar, then its direction does not change, only its magnitude change m times. Distributive over vector addition. This property will be proved when we will learn about scalar triple product. However, from this we may easily prove that A cross B minus C is equal to A cross B minus A cross C. Cross product of parallel vectors. Cross product of two non-zero parallel vector is 0 or null vector, because angle between parallel vectors is 0 and the value of sine theta is 0. From this property we may conclude that cross product of unit vectors I cap, j cap and k cap along x, y and z axis respectively with their same is like this. Cross product of perpendicular vectors. The magnitude of cross product of vectors is the area of the rectangle formed by the perpendicular vectors, and the direction of the cross product is the direction of a unit vector n, which is perpendicular to both vector a and b, such that a, b and n form a right-handed system. Here the point to be noted is that vectors a, b and n are mutually perpendicular vectors. The coordinate axes are also mutually perpendicular. So the cross product of unit vectors I, j and k with their perpendicular ones is like this. You can easily get this by using right hand rule, but there is a more easy method. Draw a circle and put arrowheads directing counterclockwise on the circumference of the circle. Write I, j, k following the same counterclockwise direction like this. Now look at the formula. The sequence followed in the formula of the first three is ijk, jki and kij, and now ijk, jki and kij sequences are all counterclockwise in this circle. Counterclockwise means positive by convention, so the result is positive in these cases. In the next three, the sequence is jik, kji and ikj, and these sequences jik, kji and ikj all follow clockwise sequence in the circle. Clockwise means negative by convention, so the result in these three are negative. Vector product in terms of components. Let vector A equal to A1 I cap plus A2 j cap plus A3 k cap and vector B equal to B1 I cap plus B2 j cap plus B3 k cap. Then A cross B is equal to this. Now we apply the properties we have already learned and we get the result. This result can also be written in determinant form like this. Area of parallelogram having diagonals represented by vectors A and B. Let ABCD be a parallelogram where vector AB equal to vector DC equal to vector Q and vector AD equal to vector BC equal to vector P. Here vector AC equal to vector A and vector BD equal to vector B. We have learned that vector AC equal to vector A equal to vector P plus vector Q, and vector BD equal to vector B, which is equal to vector P minus vector Q. Solving for P and Q from 1 and 2, we get vector P equal to half vector A plus vector B and Q equal to half vector A minus vector B. Now area of parallelogram ABCD is equal to magnitude of P cross Q, which is equal to magnitude of half A plus B cross half A minus B. We calculate it and we get that the area of the parallelogram is equal to half magnitude of A cross B. Area of quadrilateral having diagonals represented by vectors A and B. Here AC equal to vector A, BD equal to vector B. Area of triangle ACB is equal to half magnitude of vector AB cross AC. Thus magnitude of this vector is equal to area of triangle ACB, which implies that magnitude of this vector is also equal to area of triangle ACB using vector's commutative property of cross product. Now area of triangle ADC is equal to half of the magnitude of AC cross AD. This implies magnitude of this vector is equal to area of triangle ADC. When we add these two, we get the area of the quadrilateral ABCD. Now these two vectors are parallel because they are perpendicular to the same plane of quadrilateral. Now we add these two vectors. These vectors are parallel, and so we can use this formula. So we get mod of half AC cross AD minus half AC cross AB equal to mod of minus half AC cross AB plus mod of half AC cross AD, or we get mod of half AC cross AD minus half AC cross AB equal to area of quadrilateral ABCD equal to mod of half AC cross AD minus AB applying distributive property, which is equal to half AC cross BD, because AD minus AB equal to BD, which is equal to mod half A cross B. Thus, area of quadrilateral is half the magnitude of the cross product of the vectors represented by two of its diagonals. Lagrange's identity. If A and B be two vectors, then mod A cross B whole square equal to mod A whole square mod B whole square minus A dot B whole square. This can easily be proved like this.